Hi, thanks for your interest. This is Dr. Swati Agarwal. Today I would be talking about a topic that is a perspective shift of fuzzy logic to nutrosophic logic. Real world is full of uncertainties and the way human beings make decisions in such an environment has been of interest to researchers from different disciplines like biology, psychology, philosophy, engineering and mathematics along with many others. One of the prominent objectives of computationally intelligent systems is to imitate the approach and the outcome of human decision-making process while providing an understandable explanation of a possible reasoning leading to it. Such systems should, as much as possible, be able to deal with the realistic aspects of the real world information like imprecision, indeterminacy, redundancy, incompleteness, ambiguity, and subjectivity. The modeling and reasoning with uncertainty and imprecision is an important research topic in computational intelligence community. Almost all the real world knowledge is imperfect. A lot of works have been carried out to deal with such imperfect information, resulting in a number of concepts being investigated, a number of problems being identified, and a number of solutions being developed. One of the prominent, successful, and extensively researched concept used in the field of computational intelligence is fuzzy logic. The general problem that motivates this webinar is to suggest experimenting with a new entrant in the soft computing domain, that is nutrosophic logic, for research and investigation in the development of a computationally intelligent system that is able to match human mind reasoning in uncertain and indeterminate environments as closely as possible. The webinar is broadly organized in three parts. Part 1 discusses the need of perspective shift from fuzzy logic to nutrosophic logic. When we already have fuzzy logic, a hugely popular and successful concept being used in computational intelligence paradigm, first and the foremost aspect to be pondered upon is the impetus for suggested perspective shift from fuzzy logic to nutrosophic logic. After having understood the need for shift from fuzzy logic to nutrosophic logic, the next component of the webinar would focus on what advantages does nutrosophic logic have to offer to the domain of computational intelligent domain, and how can nutrosophic logic be possibly integrated in the computationally intelligent framework. Finally, the last part of the webinar highlights the possible promising areas where nutrosophic logic can be experimented. Since nutrosophic logic is relatively a nascent logic, our webinar is finally concluded by highlighting the open research challenges and questions to be addressed in this domain. Professor Zadeh had revolutionized the field of logics by proposing a novel multi-valued logic, fuzzy logic, in 1965, where each element in fuzzy set has a degree of membership. Let U denote a universe of discourse, then a fuzzy set A in U is defined as a set of ordered pairs A equal to X mu AX, where mu A is a function of A that delivers the grade of membership of X in A. In an attempt to formalize human inference, Professor Zadeh pioneered by relaxing two truth values constraints imposed by classical logic. Fuzzy logic permits gradual numerical degree of membership that ranges between 0 and 1, that is permissible here. The basic impetus for such relaxations is clear, as the environment in which natural inference takes place is full of uncertainties and assertions which are completely true or false are very rare. Fuzzy logic attempts to capture valid reasoning patterns about uncertainty. Though with weak acceptance initially, slowly it has emerged as one of these important soft computing techniques to model uncertainty in the computational intelligence paradigm. Professor Zadeh had aptly realized that it is imperative to have a decent model of semantics of human concepts and perform realistic operations than to have an awful model and perform verifiably correct operations. Introduction of fuzzy systems led making of systems which exhibit human concepts and their formalization, and thus this stimulated enormous research activity in soft knowledge processing. Though fuzzy logic concepts accounts for the nature of human concepts, but they are still limited since formal concepts are fixed in closed world and they cannot cater completely to human concepts which are developed and most importantly keep modifying in open world. So, it is quite natural that for open problems like open world of human fuzzy concepts, rigidities of fuzzy formal approach be further relaxed. Consider this example. If X is cold, then it is very likely that Y is hot. If X is hot, then it is not likely that Y is hot. What is the probability that Y is hot if X is having a medium temperature? This example gives a clear insight for conventional human reasoning systems, fuzzy reasoning systems, and futuristic human reasoning systems. Conventional human reasoning systems fail in four aspects. 1. Such systems do not offer any method for dealing with the fuzziness of antecedents and consequence. Second, for such systems, probabilities can be estimated as crisp numbers. Third, no mechanism for inference from rules in which the qualifying probabilities are fuzzy. Fourth, finally, rules which are used for composition of probabilities depend on unsupported assumptions about conditional independence. Fuzzy logic overcomes some but not all the limitations of conventional human reasoning systems to a certain extent. Fuzzy logic permits the antecedents and or consequence and or qualifying probabilities to be fuzzy. Second, fuzzy logic also makes it possible to estimate probabilities as fuzzy rather than crisp numbers. Apart from the benefits of fuzzy logic, futuristic human reasoning models need to address two very significant aspects, and they are: first, the composition of qualifying probabilities can lead to fuzzy probabilities that are inadequately precise or equally unsatisfactorily informative, thus capable of capturing indeterminacy too. Second, normally inference in fuzzy logic reduces in general to the solution of a non-linear program. So devising techniques for the solution of such programs may be computationally pricey. Currently, we do not have inexact, low-price techniques for inference from fuzzy probability qualified fuzzy if-then rules. Also, we do not have an effective method of inference from possibility qualified rules within a branch. Reviewing the points just discussed, it appears that fuzzy logic is not the final solution for representing human knowledge about the world. Rather, it is a foundation based on established notions that could easily be grasped by engineers and researchers as a step towards formalizing human reasoning. Goal of the model that reasons human concepts should be of taking partially true facts which have the element of uncertainty, vagueness, ambiguity, imprecision, incompleteness, inconsistency, redundancy, or contradiction, which are distributed over a sample space, and to build a knowledge based system that will apply certain reasoning and aggregation strategies to make useful decisions. So, it is quite expected that some more barriers be lifted from fuzzy logic before it can be applied to delicate areas of fuzzy reasoning. Till the time laws of human reasonings are understood, accommodation of paradoxes should be a crucial aspect of human reasoning model, as experimentation with the model would extend the understanding and will help to resolve them. Quite recently, nutrosophic logic has been proposed by Professor Florentin Smarandence in 1999 that is based on non-standard analysis. Nutrosophic logic was developed to represent mathematical model of uncertainty, vagueness, ambiguity, imprecision, incompleteness, inconsistency, redundancy, and contradiction. All the factors stated are very integral to human thinking, as it is very rare that we tend to conclude or judge in definite environments. Imprecision of human systems could be due to the imperfection of knowledge that human receives from the external world. Imperfection leads to a doubt about the value of a variable, a decision to be taken, or a conclusion to be drawn for the actual system. Multiple factors could lead to uncertainty, like incomplete knowledge, stochasticity, or acquisition errors. So, it is expected that the developed system should be able to handle indeterminacy that can arise due to unknown features, behaviors, and unanticipated happening conditions which are uncontrollable. Thus, a better approach would be to employ nutrosophic logic. Nutrosophic logic is an extension, combination of the fuzzy logic, intuitionistic logic, para-consistent logic, and the three-valued logic that uses an indeterminate value. In nutrosophic logic, every logical variable x is described by an ordered triplet x equal to t, I, and f, where t is the degree of truth, f is the degree of falsity, and I is the level of indeterminacy. T, I, and F are the nutrosophic components that are real standard or non-standard subsets of -0 to 1 plus. Let U be a universe of discourse and M a nutrosophic set included in U. An element X from U is noted with respect to the set M as X TIF and belongs to M in the following way. It is T% true in the set, I% indeterminate in the set, and F% false, where T varies in truth component, I varies in the indeterminacy component, and F varies in the falsity component. The sets T, I, and F are not necessarily intervals, but they may be any real subunitary subsets, discrete or continuous, single element, finite or infinite, union or intersection of various subsets, etc. They may also overlap. We use a subset of truth instead of number only because in many cases we are not able to exactly determine the percentages of truth and falsity but approximate them. For example, a proposition is true between 30 to 40% and between 60 to 70% false. Even worse, between 30 to 40% or 45 to 50% true according to different analyzers and 60% or between 66 to 70% false. A cloud is a neutrophobic set because its borders are ambiguous and each element, that is a water drop, belongs with a neutrophobic probability to the set. Also, we are not sure where the cloud ends nor where it begins. Neither if some elements are or are not in the set. That's why the percent of indeterminacy is required and the neutrophobic probability should be used for better modeling it. Indeterminacy is the zone of ignorance of a proposition's value between truth and falsehood. Another example is about rain. This proposition is, say, 50% true according to meteorologists who have investigated the past year's weather, between 20 to 30% false according to today's very sunny and droughty summer, and 40% undecided. Another example is about heap. As an application to Sorite's paradoxes, we may now say that this proposition is 80% true, 40% false, and 25 to 35% indeterminate. The neutrality comes for we don't know exactly where is the difference between a heap and a non-heap. And if we approximate the border, our accuracy is subjective. Vagueness plays here an important role. The another example is about voting. The candidate C, who runs for election in a metropolis M of 10 people with right to vote, will win. This proposition is, say, 30% true, that is 3 people voting for him, 30% false, that is 3 people voting against him, and 40% indeterminate, that is 4 people not coming to the ballot box or giving a blank vote, not selecting anyone, or giving a negative vote, cutting all the candidates on the list. Certainly, this fact cannot be represented by fuzzy logic or intuitionistic fuzzy logic. Neutrophobic logic proposes that between an idea A and its opposite anti-A, there exists a gamut of continuous power spectrum of neutralities which can be represented by neut A. Fuzzy logic, though, ensures multiple belongingness of a particular element to multiple classes with varied degree, but capturing of neutralities due to indeterminacy is missing. It is further limited by the fact that membership and non-membership value of an element to a particular class should sum up to 1. Similarly, other allied logics like Lukasiewicz logic considered 3 values, 1, half, and 0. Post considered m values, etc., but all are handicapped with the constraint that values can vary in between 0 and 1 only. Intuitionistic fuzzy logic, though, deals with indeterminacy parameter related to a particular element, but this fact is still constrained with the condition that for any element x, indeterminacy value would be 1 minus the sum of membership value and non-membership value. There is no provision of distinguishing between relative and absolute truth, indeterminacy, or falsity. In a rough set, an element x on the boundary line cannot be classified as a member of a particular class, nor of its complement with certainty, but can be very well described by neutrophobic logic, such that x is TIF, where TIF are standard or non-standard subsets of the non-standard interval -0 to 1 plus. Neutrophobic set emerges as a dominant formal framework which generalizes various other logics like classical set, fuzzy set, interval-valued fuzzy set, intuitionistic fuzzy set, and interval-valued intuitionistic fuzzy set. When the sets are reduced to an element only respectively, then the superior values and inferior values merge and they are just 1-point values. Hence, the nutrosophic logic generalizes the Boolean logic for n equal to 1 and I equal to 0 with t, f either 0 or 1. The multi-valued logic for t, I and f varying between 0 and 1. The fuzzy logic for n equal to 1 and I equal to 0 and t, I, f varies between 0 and 1. The intuitionistic fuzzy set for t plus I plus f equal to 1 and I is greater than equal to 0 or less than 1. Nutrosophic logic includes varied range of logics, so there seems a possibility of potential conversion of logic-specific systems to more generalized and indiscriminate logical systems that can exhibit different logical behaviors depending on the nature of the problem being solved, which is possible by integrating nutrosophic logic in systems. How nutrosophic logic can contribute to computational intelligence systems would be explained with a small example in medical domain. Healthcare industry has been trying to complement the services offered by conventional clinical decision-making systems with the integration of fuzzy logic techniques in them. Medical knowledge base is vast, complex, and ever-changing. It is suggested here how to investigate the use of nutrosophic logic in medical domain. Nutrosophic logic is a generalized logic and possesses all attributes necessary to encode medical knowledge base and capture medical inputs. It is understandable that no fixed treatment strategy comprising specific drug usage and other modalities of treatment can be fixed even for patients of similar nature problems. Moreover, scope of ambiguities, uncertainties, and indecisiveness in inputs to medical expert systems do vary due to history, that is, patient description of the diseased condition, physical examination, especially in cases of uncooperative or less intelligent patients, or laboratory tests due to faulty methods or equipment. Medical diagnosis demands large amount of information processing, large portion of which is quantifiable, intuitive thought process involving rapid unconscious data processing and combines available information by law of average. So, the whole process offers low intra and interperson consistency. Contradictions, inconsistency, indeterminacy, and fuzziness should be accepted as unavoidable as it is integrated in the behavior of biological systems as well as in their characterization. To model an expert doctor, it is imperative that it should not disallow uncertainty as it would be then inapt to capture fuzzy or incomplete knowledge that might lead to the danger of fallacies due to misplaced precision. Considering the above facts, it is thus suggested to use nutrosophic logic for representing medical knowledge. Possibility of integrating nutrosophic logic with medical knowledge base is reasoned on the grounds that while opting for any particular therapeutic plan, any doctor would be performing information fusion as the data would be coming from multiple sources like patient's description of symptoms, laboratory data. So to model such systems, it is essential that we should consider not only the truth membership supported by the evidence, but also the falsity membership against the evidence. As shown in the figure, nutrosophic logic would help in explicitly listing out three important components of the input values captured: truthness, indeterminacy, and falsity. Figure shows the conceptual membership functions of blood sugar level equal to normal, which are designed for capturing truthness, indeterminacy, and falsity of the input recorded. The designing of these three membership functions would vary considerably for different parameters. Here in this figure, the captured input I is mapped onto the three membership functions. It is assumed that indeterminacy related to deciding whether the blood sugar is normal is high on the tapering ends of the truth membership functions designed. Falsity membership function corresponds to the lab equipment error or degradation of equipment noticed, which can give erroneous results. So, according to the figure, the three component values generated after nutrosophication of captured input I is T1, I1 which is equal to 0 and F1. The next figure discusses the nutrosophication process applied to multiple parameters simultaneously. As it is very common in medical domain to infer diagnosis D, analysis of multiple parameters is required. Here in the figure, it is assumed that analysis of four important parameters is required to infer D. As clearly shown, input parameter I1 lies in the indeterminacy zone, which could be possible due to lack of information or early onset of disease during which input I1 cannot be captured. And input parameters I2 and I3 lies in the truth zone, indicating favor for D. Corresponding mapping of I1, I2 and I3 onto y-axis shows that I3 favors strongly for D in comparison to I2 as T1 is greater than T2. Input parameter I4 contradicts the possibility of D by F1 value. Fuzzy logic designs not only the truth membership functions that gives description of degree of membership value to a particular class. Contrary to fuzzy logic, in which there is no provision of capturing indeterminacy corresponding to non-availability of information or falsity functions to record the imprecision or degradation of the equipment with which input is captured, Nutrosophic logic is definitely a better representation of the medical data as it gives the clear insight of the truthness, indeterminacy, and falsity associated with the input captured. This should indeed be of considerable interest to the medical AI community because, as indicated above, medicine is essentially a continuous domain where the captured inputs can have uncertainty, indeterminacy, and sometimes falsity associated. Incorporation of nutrosophic logic in the medical models would retain the continuous behavior as displayed by the fuzzy logic also. Such systems would essentially reduce to medical systems with fuzzy logic under special circumstances. Medical domain is the field where there is indeterminacy, unknown hidden patterns, imprecision, high conflict between sources of information, non exhaustive or non exclusive elements of the frame of discernment. So, Nutrosophy is a potential candidate for representing these elements. The proposed Nutrosophic logic theory is not a substitute for existing fuzzy medical models, but an extension and enhancement of classical AI approaches. Due to inherent advantages of Nutrosophic sets, such systems would address medical problems more adequately. What makes inclusion of Nutrosophic logic in the medical domain as a powerful tool is because of its desirable properties of allowing continuity, gradation of reality, capturing of truthness, indeterminacy, and falsity. Though a trade off needs to be done between what is important currently, novel and more accurate sources of acquiring data, or developing new reasoning techniques to deal with the available data. But certainly, second option seems more viable when imprecision, uncertainty, and gaps are integrated in the medical data acquired. Nutrosophic inference is a computer paradigm based on nutrosophic set theory, nutrosophic if-then rules, and nutrosophic reasoning. Similar to fuzzy inference systems, the basic structure of a conceptual nutrosophic inference system would consist of 5 components. A nutrosophication module that transforms the crisp inputs to degrees of matches with linguistic values, a nutrosophic rule base that is comprised of nutrosophic if-then rules, a database or dictionary that gives the membership functions of nutrosophic sets used in nutrosophic rules, a reasoning mechanism that performs the inference procedure using the nutrosophic rules, a given condition to derive a reasonable output or conclusion, and finally, a denutrosophication module that transforms the nutrosophic results of the inference system into a crisp output. Nutrosophic inference systems can accept either nutrosophic inputs or crisp inputs, but the generated outputs are almost always nutrosophic sets. When using a nutrosophic inference system as a controller, it is essential that a crisp output is generated. A denutrosophication method can be utilized to generate a crisp output that best summarizes a nutrosophic set. A nutrosophic inference system with crisp output is schematically shown in the figure. The boundary indicates the basic nutrosophic inference system with a nutrosophic output. Nutrosophic logic is relatively a new logic. Due to its inherent generalizations, Nutrosophic logic can be applied to a wide range of fields such as decision making, information fusion, medicine, military, cybernetics, and physics. Pattern recognition, economics, data analysis, and other areas that involve high levels of uncertainty, complexity, or non-linearity would be suitable platforms for experimenting with Nutrosophic logic. Some promising applications include electronically stabilized camcorders, autofocus camcorders, washing machines, air conditioners, automobile transmissions, subway trains, and many more. To summarize, Nutrosophic logic lays a platform which can be researched in areas ranging from industrial process control based databases, e commerce, stock market prediction, and medical diagnosis. This type of logic can be applied invariantly to any domain that experiences gaps in information and where information is incomplete, incoherent, and inconsistent. Soft computing provides a computational framework to address design, analysis, and modeling problems in the context of uncertain and imprecise information. Components of soft computing, that is, fuzzy logic, neural networks, and genetic algorithms, share a symbiotic relationship rather than a competitive one. Thus, the hybridization of two or more techniques have always been proved as more effective one in comparison to one isolated technology. Hybridization of two or more techniques have usually generated better results. So, to augment the capabilities of this generalized Nutrosophic logic, the hybridization with other soft computing techniques like evolutionary computing, genetic algorithms, neural networks can be tried and experimented. Largely, neuro-nutrosophic hybridization can be researched prominently in two ways. First, a neural network equipped with the capability of handling nutrosophic information, which is termed as nutrosophic neural network. Second, a nutrosophic system augmented by neural networks to enhance some of its characteristics like flexibility, speed, and adaptability. Though genetic fuzzy systems have been successfully applied in varied domains, this webinar suggests the integration of genetic algorithms to nutrosophic systems, which are more generalized as compared to fuzzy systems. Though genetic fuzzy systems have been successfully applied in varied domains, this webinar suggests the integration of genetic algorithms to nutrosophic systems, which are more generalized as compared to fuzzy systems in representing and capturing indeterminacies and gaps of data in the form of genetic nutrosophic rule-based systems, such that genetic process learns or adapts different components of nutrosophic rule-based systems. The major driving force for suggesting this hybrid combination is the development for inexpensive solutions that would utilize intelligent tools for information processing, design, and optimization. Genetic nutrosophic rule-based systems would be much more generalized and efficient in processing real-world uncertainties in comparison to their fuzzy counterparts, as nutrosophic logic is much more effective in representing and capturing indeterminacies and gaps present in the real-world information. Augmenting evolutionary learning capabilities in the form of genetic algorithm to genetic nutrosophic rule-based systems would certainly cut cost and time required to design, allowing independent operation, and would maintain systems with a high degree of machine intelligence for control, prediction, modeling, and decision making. Future research should focus on establishing practical applications for the proposed models and developing computer simulations for those models. Since nutrosophic logic is a new logic for which sound mathematical working fundamentals have yet to be established, so a lot of research with respect to establishing sound mathematical base that guides the working of any nutrosophic logic based inference system is required. Then only the potential of such a powerful logic can be tapped for any real world application. It is believed that this webinar would help the viewers in understanding that how effectively nutrosophic logic can contribute to the discipline of data analysis with knowledge for improvement in practical applications. It is hopeful that further work will be continued in order to solve many other real life problems. Due to the reasons explained, definitely nutrosophic logic holds its chance to be further researched and experimented for utilization in real-world executions and human psychology simulations. Thank you for watching.